Hello, everyone. Welcome. So we're very happy to have Yelena Mandelshtam here to tell us about crossing the transcendental divide from Riemann surfaces to algebraic curves. And how would you like to ask questions?
Um, so I guess if it's a time sensitive question, then just unmute yourself and interrupt. Maybe actually raising hands would be good, but if I'm not like noticing, then just unmute and interrupt. Um, what's the transcendental divide? Good question. So there's a lot of words in this title that I'm aware many of you might not have learned yet. And in fact, the transcendental divide is a kind of made up name. So I will tell you about all of these words. So don't worry if you don't know them yet. And I will tell you about the transcendental divide. But I guess a summary of what the transcendental divide is in so Riemann surfaces and algebraic curves are two kind of mathematical objects with different definitions. Turns out they are the same thing, but between them, there is a big divide, which we call the transcendental divide. I'll say more about that later. All right, so yeah, and as I said, questions are good. I hope to make this talk very understandable, but if anything is unclear, I would be very happy if you interrupted to ask me a question. Okay, so we'll start with some opening words. So a lot of people believe that math can be divided into two categories broadly. So into analysis and algebra. And analysis primarily deals with continuous things, infinity, and it has techniques to study problems in analysis that are different from algebra, which focuses more on the study of mathematical structures. Some examples of these are written here, right here. But and these are usually discrete structures as opposed to continuous, and with strictly defined relationships that are defined by equations and operations with rules of how you work with them. And so in general, if you pick a subject, often it'll fit kind of mostly in one or two of these categories, or it'll have two sides of it. For example, number theory, you might hear that there's analytic number theory, which uses analytic techniques to tell us things about distribution of prime numbers, for example. And then there's algebraic number theory. And that helps us a lot with things like factorization. So both of these tell us about numbers and prime numbers, but algebraic number theory and analytic number theory have very different techniques to answer questions. But both of them can tell us something about number theory. And there's a lot of jokes about analysts versus algebraists. A lot of mathematicians will self-classify themselves as analysts or algebraists. There's even, I guess, this mathematical lore that how you eat corn can predict whether you're an analyst or an algebraist. So if you eat it in rows, like a typewriter like this, and then you eat the next row, apparently that means you're an analyst. And if you eat it in spirals, you're an algebraist. Or I've actually also heard it said in the other way around. So I don't know how much truth this has, but apparently it's supported by some anecdotal evidence. So if you're interested, you can read more about that. Some mathematicians have written blogs about it. But I would like to argue that actually it is some of the best and most interesting and most amazing math happens when we're able to make these two things come together. And especially when we're able to use algebra we're able to use things from algebra to help us figure things out in analysis, or vice versa. And in general, it's really good if these two sides can talk to each other well, because if we can use some insights from analytic techniques to tell us more about the algebra things, that's good. More tools is always a good thing. All right, so one subject that I guess broadly falls under the category of algebra, and a hint for that is that it has the word algebraic in it, so often that'll be a clue. I don't know what geometry with a bunch of question marks means, so I'm gonna ignore that question. But algebraic geometry, some people say, kind of lies in between, because it does use some things in analysis. So algebraic geometry is very big. A lot of people believe very hard subject. People spend years studying it. So I'm not going to answer this question in full in one slide, but I'll tell you a little bit. So it's a branch of mathematics that studies solutions of polynomial equations using algebra and geometry. And so the key objects here are called varieties, or algebraic varieties. And these are shapes that are defined by algebraic equations. So even if you didn't already know what a variety was, you are familiar with at least some of them. So I could write down a polynomial, x squared plus y squared minus 1, and ask where it's equal to 0. And so, if we move the 1 to the other side, we get x squared plus y squared equals 1. And hopefully you recognize that that is this circle right here. So this circle is the shape, and this is the algebraic equation that defines it. And this lives in the xy plane. We can also write down y minus 2x plus 1. That's a very simple variety that just looks like a line. Now, with these two things, we can do slightly more complicated things. So here's a more complicated polynomial, x squared plus y squared minus 1 times y minus 2x plus 1. So this is just the product of these two. And it's equal to 0 when either one of these factors is equal to 0. So this factor is equal to 0 when we're on the circle. This factor is equal to 0 when we're on the line. So either one of them will be equal to 0 when we're either on the circle or on the line. So the variety will be the combination. So it'll be this thing right here, the circle and the line. We can also define the variety by more than one equation. For example, here we could ask x squared plus y squared minus 1 to be 0 and y minus 2x plus 1 to be 0. So both of them are 0 when we're on the circle and we're on the line. So the variety will be the 2 points of intersection between them. And so I drew a bunch of varieties that live in the xy plane, but we can also include more variables, and then we'll live in higher dimensional planes. So here with 3 variables, we'll have a variety that lives in 3-dimensional space. Let's think about what's going on here. So we have x squared plus y squared plus z minus 1 equals 0. So when z is 0, then we just have x squared plus y squared minus 1 equals 0, so a circle. So when z equals 0, we have a circle. So we could maybe say the z-axis will be vertical, and then, okay, maybe I'll just draw it. The z-axis will be vertical. And then at z equals 0, we'll have a circle of radius 1. Maybe let's see, when z equals 1, then we have x squared plus y squared equals 0, which only has real solutions when x and y are both 0. So when z equals 1, we just have a single point. And then as z decreases from 1 to 0, so like if z is 1/2, for example, then we still have a circle, just the radius is getting smaller. So we'll have circles whose radius is getting smaller and smaller and smaller until we reach just the point. So we have a cone up here. And then of course, Z can also be negative. And if Z is negative, then we're increasing the radius of our circle. So it'll be this infinite cone. And the variety will be the surface of this cone. So all the points on the surface of it. So this is going to be a two-dimensional variety living in three-dimensional space. And as you might be able to imagine, hopefully, the more complicated we make these polynomials, the more of them we have and the more variables we have, which means we live in higher dimensional space, the more interesting these shapes can become. So we can get all kinds of shapes you can imagine. And algebraic geometry is the study of the geometry of these shapes. So figuring out properties of these shapes based on the algebraic equations that define them. That's a summary of this field of math. Any questions so far? All right, then I'll talk about, okay, so here's a better picture, I guess, of the variety that I just drew for you. All right, so a subset of algebraic geometry is the study of very specific algebraic varieties. So these are algebraic curves. So an algebraic curve is a variety of dimension 1. So when I say dimension 1, I mean it looks like a line that has been like bent out of shape somehow, or multiple lines. So it doesn't look, you don't have any two-dimensional pieces anywhere, and a two-dimensional piece would look like not a line, a filled-in shape. So if we go back up here, my one-dimensional varieties are this one, this one, this one. This one is not one-dimensional, this one is zero-dimensional, because we consist of discrete points, which are zero-dimensional. And this variety here is two-dimensional, because we do have filled-in two-dimensional pieces. So algebraic, so these three things right here, these are algebraic curves, the other two are not. So it's a variety of dimension 1. So yeah, another example, it's not on the previous slide, would be a parabola. Y given something like y minus x squared equals 0. We can also write down like y squared equals x cubed plus ax plus b. And then depending on what a and b are equal to, this will look like one of these three things. So it can be one piece that looks like that, or under the right conditions for a and b, it can do a self-intersecting loop like this. This is actually considered not smooth because here we're not smooth. And then on the other side of that, so your A and B get closer to satisfying the condition for them to intersect, and then they intersect, and then as you move them, as you change A and B more, then this piece will detach and we'll have two pieces. And these kinds of curves are called elliptic curves, and they're very interesting to number theorists, and just in general, a lot of people study just elliptic curves. So even within this specific part of algebraic geometry where we study algebraic curves, we can go even more specific and study elliptic curves. So the books can be filled with things that we know about, many books can be filled with things that we know just about algebraic curves or just about elliptic curves. And even more books can be filled with things we don't know yet. So I see a raised hand. Do you want to ask your question?
Miss, when you said that in the middle curve, the intersection, you said it's not smooth. You mean in the sense that the high derivatives aren't continuous?
That is, yeah, so that is something I mean there. When I was saying it, you don't need to know that that's what it means. It's just an example of something. I mean,
But
you can.
I didn't understand. How is that possible if it's just a polynomial? Like, aren't polynomials differential? Like, all the derivatives are differentiable everywhere, or not?
Well, so that's so it's not really the derivatives of this particular polynomial.
Oh, okay. Is it like something else you're referring to? Can you talk about smoothness?
Yeah, so so in general, you can have I guess what are called singularities on the curves, which can look like a self-intersection or just anything kind of pointy. So
Okay.
this
Thank
is
you.
also defined by algebraic equations, but
Okay, got it. Miss. Thank you.
yeah, mhm. Sorry, it's defined by polynomial equations. All right, so these things I drew. Oh, I see a raised hand. Do you want to ask your question?
If a variety is one-dimensional, does that mean it's defined in terms of two variables?
Not necessarily. So that's the next thing I was going to get to. So if it's defined in terms of two variables with just one polynomial, it'll be one-dimensional. But
Multiple polynomials, then what happens?
so if it's in two dimensions with multiple polynomials, usually you'll get a zero-dimensional variety. But if you start out with more variables, you start out in a higher dimension, and then you'll need more polynomials to define a one-dimensional variety. So here you see we started in a three-dimensional space. We have one polynomial, and we end up with something two-dimensional. So if we have, if we added another polynomial, most of the time, another polynomial would kind of cut this. So as you can see, if we had multiple polynomials, we kind of look at where they intersect. So we can cut it by another polynomial. And then, for example, if we just defined it by an easy polynomial, z equals 0, then what we end up with is a cross section, just this circle right here, which is now one-dimensional. So usually we'll need, if we have d variables, we live in d-dimensional space. If we have d minus 1 polynomials, most of the time we'll get a one-dimensional variety. So Tony, you said if you have n polynomials, the maximum dimension is n minus 1. Well, yes. Yeah, if you have one polynomial, you always will drop dimension. If you have more than one polynomial, you won't necessarily drop dimension for each polynomial. All right, so Pranav, I see you're still raising your hand. Do you still have a question or?
One more thing, it says, if the number of polynomials plus one is equal to the dimension, that's an algebraic curve. If the difference is one, it's an algebraic curve.
Not necessarily, because you might have situations where it's not true that each polynomial causes the dimension to drop by 1.
Yeah, but that's only if the polynomials are not linearly independent.
That's also not quite true. So yeah, so you can read about this. A keyword here is complete intersection. But yeah, I think I should move on. So yeah, so I see people are answering questions in the chat. I'm happy about that. So yeah, the cone is a two-dimensional because we're really only looking at the surface of the cone, not the inside. So two-dimensional shape means that we have filled two-dimensional pieces, which we do, but we don't have filled three-dimensional pieces. All right, and so yeah, so here I'm drawing, so it's a lot easier to draw curves in the plane because that's how I draw things. But we can have curves living in any dimension, as I said. So here I attempted to draw a three-dimensional curve, which is actually smooth. So imagine that these pieces aren't pointy at all. And this isn't a self-intersection because we're in a three-dimensional plane. So imagine this kind of piece going behind, like a spiral behind the curve. And so this curve in three-dimensional space. And you can imagine if we're in super high dimensional space, we can also have very interesting looking curves. Pranav, do you still have a question? No, okay, great. All right, and so as I said, there are many, many things to know about algebraic curves and many things that people still don't know. It's still a very active area of research. All right, so now we'll shift over. So these are things that live on the algebraic side, as you might have guessed, because of the word algebraic, but also we're really defining things using polynomials. But the geometry of these objects, so when we say algebraic geometry, the geometry of this geometry is often a more analytic thing. We're looking at, as I said, we are interested sometimes in smooth curves that deals with differentiation, which is an analytic thing. So algebraic geometry does use things from both algebra and analysis, definitely. All right, but on the more analytic side, we have a manifold. So what is a manifold? I'm not going to give you the official definition, but it's something. So a topological space, if you don't like when I say topological space, just think a thing that locally looks like R to the n, so the Euclidean plane. What I mean by this is that if you zoom in enough on your thing, then on your manifold, then it looks flat in whatever appropriate dimension you're working in. So an example of this is a circle, which is a one-dimensional manifold. So if I zoom in enough on the circle, which I actually did here, and I get this piece, if I zoom in even more, so I can zoom in as much as I want, eventually it'll just look like a one-dimensional line, which is just R to the 1. So this is an example of a manifold. A two-dimensional manifold would be the surface of a sphere. So you take a sphere like the Earth, which is approximately a sphere, and then you zoom in enough on some area of it, it'll look flat, like a two-dimensional plane. These are maybe very simple manifolds. You can also get more complicated, interesting ones like this other two-dimensional one called a Klein bottle, where also if you zoom in on any one piece of it, if you zoom in enough locally, it will just look like a piece of the flat plane R2. All right, and so these are, of course, there's many things that people study about manifolds. The fields that study these will mostly be in analysis. And then within that, we can study Riemann surfaces. So a Riemann surface is a manifold of complex dimension 1. So this means, manifolds and topological manifolds, I believe, are the same thing. When you study something like topology, you might study something called algebraic topology, and then you'll be using certain techniques for it. But all these things can be translated to each other in theory. All right, so a manifold of complex dimension 1 means that if we zoom in on the manifold enough, then eventually it will look like the complex plane. So hopefully you've seen this, that the complex numbers, we can put them in a plane called the complex plane, like this, where we have a real axis and an imaginary axis. And so the real number 1 lies on the real axis, the purely imaginary number I lies on the imaginary axis, and then other numbers that have real and imaginary parts lie somewhere in the plane. So like 2 plus 2i we'd plot here, 1 minus I would go here. And if we take all the complex numbers, and that fills up this plane. So complex dimension 1 can be thought of as real dimension 2. And these are, in some sense, kind of your simplest manifolds, or I mean, they are your lowest dimensional manifolds, because often we like to work with complex numbers. So they're your lowest dimensional manifolds that are interesting to study. But still, even though they're the lowest dimension, there's still many books that can and have been filled with information we know about Riemann surfaces, and many books to be filled with things we have yet to know. And so some examples of these Riemann surfaces are the sphere. So this isn't a circle, this is the surface of the sphere. Like I described before, we get this donut called a torus, where we could glue two of the tori together. And we can do this process. So these are examples of Riemann surfaces. All right, and so a punchline here, and maybe the title of my talk or the abstract of it, or so far you've seen some clues that Riemann surfaces and algebraic curves, it turns out they are actually the same thing. So on one side we have manifolds that have dimension 1. On the other side we have varieties that have dimension 1. And these are actually the same thing, and this goes back to a theorem from the time of Riemann, so hundreds of years ago. Yeah, very long time ago, people have known this. And so the Riemann surface is the analytic name for this object. Algebraic curve is the algebraic name and definition for these objects. They do have different definitions and different properties, and this is not in any way an obvious relationship. In fact, them being the same thing, if they're really the same, then when you ask someone to tell you some algebraic curve and they bring you a Riemann surface, if they were really the same thing, you'd be happy about that. But really, I think of it as more like you go to a restaurant and you order some French fries and someone brings you a potato and says, well, they're the same thing. So they're not, they are the same thing, but you need to do some work before you can really translate one to the other. And the talk will be about this. So the reasons why we might want to do this, so as I said, algebraic curves are very well studied, and with also still lots to study. Riemann surfaces also very well studied with lots to study. And of course, since they're the same thing, it would be ideal if anything we proved about Riemann surfaces, any theorem we proved about Riemann surfaces immediately became a theorem about algebraic curves and vice versa. So sometimes that does happen. Sometimes there's a lot of work that you need to do it. And there are some things that are easier to do analytically, some things that are easier to do algebraically. So if we had very good ways to translate between the two, that would make it easier to decide if something, so start out studying something on the analytic side, then decide that something about it is easier to prove algebraically, and then you move to the algebraic setting, do it there, and then you can take it back. So ease of moving between the two would be very good for a lot of mathematicians. Unfortunately, in practice, it's very hard. So the theorem that proves that these two are the same, it's not constructive. It doesn't really give you a recipe that you can follow to get from one to the other. And so some of the research I'll be telling you about is how we tried to work on getting a little bit closer to being able to do that. Okay, so before I tell you about that, I'll tell you about an important property of algebraic curves or Riemann surfaces called genus. So genus has, there are different ways that you can give a definition of genus, but the easiest one and the easiest one to see for a Riemann surface, it's the number of holes that your Riemann surface has. So here the genus is increasing. For a sphere, it's 0. It has no holes. For the torus, it's 1. For this double torus, we have 2 holes, 3 holes, so on. And so genus is a very important metric. It already tells you a ton about your surface. So it's all curves of genus 1, of course, they're not the same. We can have a torus that looks like that, or we could have some really crazy looking shape with a hole. And these are, of course, different Riemann surfaces, but they both have genus 1, so there are some things that will necessarily be true about both of them at the same time. And a lot of results about Riemann surfaces or algebraic curves are separated by genus. So they depend on, the theorem might depend on the genus of the thing you're talking about. So the number of holes is something great. It's something you can just look at your Riemann surface and see what the genus is most of the time. So other definitions are harder. You can't really just see them. And for a curve, an algebraic curve, you really can't just look at an algebraic curve and know its genus, unfortunately. So there's no such thing with number of holes that you can really do with an algebraic curve, just based on its appearance. But the genus records other things. So a very important thing is that it also records the number of independent one forms, which are a special kind of function on your space, so on your surface. So I won't be explaining what these are, but if you feel inclined, you can read up on this later. It deals with homology and cohomology. So, but yeah, it records the number of independent special functions on the surface. So, and the idea is as your surface gets more interesting and gets more holes, then there's more things that your functions can do. So that's why as your genus increases, you also get more of these functions, but it's actually, so if your genus is G, then you have G independent one forms on your surface. And it also records similar information about a curve that I won't be describing because the definitions are complicated, but the genus is also a very important invariant of an algebraic curve. And also results about curves are split up by genus. But the general heuristic that you can use here is that as your degree goes up, which means your curve gets more complicated. So, and by degree, I mean here, so sometimes I mean the degree of the polynomial that you're using to describe your curve, but if you have a lot of polynomials, it's something a little bit different, but it is related. So the degree is a measure of how complicated your curve is. So generally, as your degree goes up, your curve gets more curvy and is doing more things. And as a general rule, as your degree goes up, your genus goes up as well. And in some cases, there are even formulas that describe this relationship. You can read about the degree genus formula if you're curious about it. Solution to dive. So yeah, I don't actually know about this. Maybe maybe Simon does. For the question in the chat. All right. But yeah, so again, genus, there are many things I can say about this, but hopefully this is an appropriate summary. Oh yeah, that is true. Curves of genus at least 2 have only finitely many rational points. So that's why, as I said, elliptic curves are very interesting to number theorists. Elliptic curves are the curves that look like this, that I described, I guess, on this earlier slide. And so rational points on elliptic curves, these are curves of genus 1, and rational points on elliptic curves are very much of interest to people. All right. So yeah, so genus is an important thing, an important metric that connects, or that of Riemann surfaces and of algebraic curves. Okay, so now we get to this question: how do we find the curve associated to the Riemann surface? So even before I ask that question, so when I say find a curve associated to a Riemann surface, I'm imagining a situation where someone gives me a Riemann surface, and then I have to do something with it and give them back a curve. But before we even answer that question, we have to think about how someone would tell me a Riemann surface. So I phrase this as, how do you email someone a Riemann surface? So if I email someone an algebraic curve, I can do that. Does anyone have an idea how I would email an algebraic curve? Just unmute yourself or send it in the chat.
Could you just like send the relationship that documents it, or is that too simple? Like the exact
Yeah, the
equation.
polynomials. Exactly. Yeah. So that's easy. If I want to tell someone an algebraic curve, I can just, yeah. So you send the polynomial. So when I see someone said zeros of the curve, so the curve is actually the zeros of the polynomial. The curve is given by the zeros of the polynomial. But yeah, usually I can just write down the polynomials, and that way they know exactly what curve I'm talking about. So a picture could so if I send a picture, that picture better be really, really exact. And sometimes actually from a picture, it might not be very easy to find out what the exact polynomials are. I mean, in general, it's not easy to find out what the polynomials are. It's actually more informative to send the polynomials, because from there you can get the picture. And also, if I'm working in 15-dimensional space, you can't really send me a picture of a curve in 15-dimensional space that I will be able to understand. So really, you can email someone polynomials, and that way you describe a curve. Yeah, so a Klein bottle filled with water, that's funny. Yeah, so if you send someone a Riemann surface, you can mail them a Klein bottle. I don't know why it would have to be filled with water, but you can mail them the exact Riemann surface. So that would be a way, but you can't really email the actual Riemann surface, unfortunately. So something you can do, some way that you can email a Riemann surface is if you email them a translation surface. So translation surface is it's a class of Riemann surfaces, very good for generating examples, because how you define them is you draw a polygon in the complex plane, and then you say which sides you identify by translation. So an example of this, which some of you have maybe seen before, is if I draw a square in the complex plane. So you might have seen this without it being in the complex plane, but just if you draw a square and then you identify its opposite sides, so pink with pink and blue with blue. But here it originally comes from the complex plane with endpoints 0, 1, I, 1 plus I. And then I identify them. So first, when I identify the blue pieces, that kind of turns into a tube. I glue them together, and then I want to glue together the pink pieces, which are these. And then as I glue them together, I get this torus, the surface of the torus. So that's a way. So this I can email. I can say the endpoints of my polygon are these ones, and then the sides that I identify are these sides. So you can go as complicated or crazy as you want with your polygons. You just need to say which sides get identified, and then you get different shapes. And of course, not every, so if I draw this square, then that's different from drawing a rectangle, for example, with endpoints 0, 3, I, and 3 plus I. So are all surfaces of the same genus homeomorphic to each other? So if they're smooth and orientable, yes. So yeah, that's that you'll learn kind of early on in your topology class. But that's a big theorem. So that's I guess an example of how genus is a very important identifier of your surfaces. But in this case where I'm not really considering all genus 1 surfaces to be the same. I actually think that genus 1 surfaces can be different from each other, and that depends on how you draw your original polygon in the plane. Well, so The thing here is that I get a Riemann surface, exactly. So the question is, would this work with any plane other than a complex plane? So if I start in the complex plane, then any piece, it's actually really easy to see that this satisfies the definition of a Riemann surface, or it's easy to see that it satisfies the definition that I gave you, because any piece of this is actually just a piece of the complex plane. So therefore it is a manifold of complex dimension 1. If I start with something else, then I'm maybe not actually a piece of the complex plane. But there are, I guess, things you could probably do with other planes, and some of the things would still be true. Okay, and so now we know at least how someone is emailing me a Riemann surface. So they'll email me a translation service, and then hopefully I'm gonna be able to do something with it and then email them back an algebraic curve. And so I will say this is still something that is very hard to do in general. For a given figure, does the manifold we get depend on which two pairs of opposite points we choose? Yes, for sure, it does. That depends on the open sets here. So here, if you've heard of open sets, if I draw like a circle inside, then it'll still be a circle over here. But sometimes if I draw a circle over here, it might actually go, it might have, if I try and bring it back to the square, then it'll lie on a boundary. So like this circle right here that gets split between these two boundaries. If I we're identifying other sides, then my boundary might look like that or something. So of course it does give you a different thing, and actually it might not even give you the same shape. In general, if you pick a given polygon, you might get just a different shape if you choose different sides to identify. Okay, so now so I'll let you think about what can happen with different shapes. So it's actually really fun to play around with. So I'll let you do that on your own. All right, so now I will give a loose definition of a Riemann matrix. So I have not told you enough things for you to be able to really understand this definition. But if you think that you're interested in it, you can read about it more later. But this is a matrix. It's G by G, where G is the genus that records important information about your Riemann surface or your algebraic curve. And I'll try to describe that important information here, but one piece of important information that automatically gets recorded is the genus. And it's very easy to see from the Riemann matrix, because it just, if your Riemann matrix is 2 by 2, you know the genus is 2. So it already has that, but it has even more information than that. So the matrix has complex entries, and it records something called the periods of your Riemann surface. So again, I'll define it in terms of Riemann surfaces, but this also has, you can also get it from the algebraic curve, and there's a definition for it. Okay, and so the Riemann matrix comes from the period matrix originally. So period matrix is G by 2G, and how you get it. So in a genus G surface, you have 2G cycles that are independent. So for each pole, so a genus 3 surface, for example, will look generally like this. And then you have 3 cycles that go around each piece of the donut, and you can see that they're independent, as they're not homeomorphic to each other, because you can't really, you can move the cycle around and bring it like here, but you can't actually turn it into alpha 2 without without actually changing your cycle. And also you have 3 cycles that each go around the hole. So I'll call the first cycles the alpha cycles, and the other ones are the beta cycles. And so of course you can choose different alpha cycles, but you have 2G independent ones. And then, as I said on an earlier slide, the genus G also records the number of one forms, which are special functions on our surface. So we can call them omega 1 to omega G. And so then if you've seen integrals before, then you may have seen integration happening from like some number to some other number. But turns out you're just doing integration along a path. So when you're integrating from 0 to 100, you're integrating on a path on the real numbers that goes from 0 to 100. But you could also integrate on a path on your Riemann surface. So this isn't a chain of integrals. These are separate entries. So it's a G by 2G matrix. So it's just a single integral. We're integrating each of our one forms, each of our functions on each path that we have. And so if you haven't seen integration, just it's a process that you do given a path and a function, and you get a number out of it. Each one form is not associated with a specific genus, but as I said, we kind of, as our surface gets more complicated, then our one forms can, or our functions have more freedom of things that they can do on our more complicated surface. So that's why we get more of them. So you can't really associate each one form with a specific, like, I assume when you say with a specific genus, you mean with a specific like hole in your surface. So it's not really like that. But kind of on each cycle, you integrate each one form, and this gives you a big G by 2G matrix. But as I said, there are choices you can make. So I could have, instead of choosing this alpha 3, I could have chosen this alpha 3. And then I will get different numbers when I integrate these on the different alpha 3. And also the G1 forms, I actually don't have just one way of picking G1 forms. These are actually a basis of a space of functions. If you've heard those words before, but if not, just there are choices that we make, and then we'll get different matrices, but they all do represent the same surface. But one kind of normalization that we can do is fix this part to be the identity matrix. So we can do a row reduction. So turn these all into ones, these into zeros, and then we get something that's left here that's a G by G matrix, and that's the Riemann matrix. And that is still, so this is a unique identifier. So again, the Riemann matrix, unfortunately, it still won't be unique. You can still have different choices that'll give you different Riemann matrices for the same surface or for the same curve. And they're related by some, they have a complicated relationship that's hard to describe. But given a Riemann matrix, there is only one surface that is related to it. So this is, even though the Riemann matrix isn't unique for a Riemann surface, the Riemann surface is unique for a Riemann matrix. So in theory, if someone gives you a Riemann matrix, in theory, there is only one Riemann matrix, or sorry, only one Riemann surface that you can give back that is related to this Riemann matrix. Unfortunately, this is also something that's very hard to do in practice. So in practice, given a Riemann matrix, it's very hard to tell you what the Riemann surface is. And in fact, it's sometimes even hard to, it's actually, it is hard in high genus, in genus at least 5. Nobody actually knows yet how to definitively say whether a Riemann matrix, whether a G by G matrix that someone gives you is actually a Riemann matrix of a curve or a surface. Sure, I guess. Yeah. Maybe I haven't haven't thought about it. But all right. So and what I'm referring to there with even determining whether a matrix is a Riemann matrix of a surface, that's called the Schottky problem. It's a very classical problem in algebraic geometry, and it is not known. Yeah, not being able to tell. So that's so yeah, I'm answering the question that just came into the chat. So it's not impossible to do so yet. It's at the Schottky problem, which asks you to determine which matrices are actually Riemann matrices. This is solved for genus 4, and then for genus 3 and below, all matrices are Riemann matrices. For genus 4, not all of them are, but we know exactly which ones are. For genus 5 and above, this just hasn't been solved, and as the classical problem, it's been open for a long time and been attempted, and progress is made towards it occasionally, but it's still unsolved and it's considered hard. All right, but yeah, so it's related to that, but so there should hopefully be some techniques that can be developed for recovering the Riemann surface or the algebraic curve from the Riemann matrix. And in fact, this is an active area of research that does have advances made every couple of years. People do write papers about how to recover a curve from a Riemann matrix in a specific genus, or if certain conditions are satisfied by your matrix. All right. So yeah, so I guess I'll tell you now a little bit about my research. I don't have so much time for it, so I'll go kind of quickly. But the idea is building on all of these. So as I said, a lot of people have studied different parts of this. So going from a Riemann surface to a Riemann matrix is non-trivial. Going from a Riemann matrix to an algebraic curve is in general hard, but done in some ways. So we put a bunch of these things that people have done together and actually try and do it in practice. All right, and before I do that, I guess I'll tell you about the L shape, which is a translation surface that starts off in the plane looking like an L, and you identify opposite sides. So you may have seen the formula V minus E plus F equals 2, vertices minus edges plus faces equals 2. So the formula, so this is true for polyhedra, for convex polyhedra. But secretly, the formula is actually vertices minus edges plus faces equals 2 minus 2g. And actually, you can do this kind of, if you're in a higher dimensional space. I mean, we don't really care about that because we're working with Riemann surfaces, but if we're in higher dimensional space, you can just do an alternating sum of all of your kind of vertex, edge, and face type things, and you get 2 minus 2g. Okay, you get the Euler characteristic. And so in our case, the Euler characteristic is 2 minus 2g, where g is the genus. And so why this is true for convex polyhedra is because those have 0 holes, so the genus is 0, so it's just not included. But from this formula, we can figure out what the genus of this shape should be. So edges, we have 4 of them. We have this pink, red, blue, and purple. So we have 4 edges. We just have one face. It's just this whole thing, kind of one face, because we're gonna end up as just one. So the outside is the face. This is the outside, but maybe we'll do the vertices first, and then that'll the stuff outside the L. Well, that's not part of our surface. But let's do the vertices. So let's look at this vertex right here at 0. So this is the bottom of the pink, so it's identified with the bottom of the pink right here. The bottom of the pink is the right of the red, so that's identified with this here. Well, that's also the top of the pink, so that's identified with this point here. That's the bottom of the purple. It's the same as this bottom of the purple. That's the left of the red, so it's the same as this one. And that's the right of blue, which is the same as this one. And that's the top of purple, which is also the same. So here, actually, we only have one vertex. All of the vertices get identified. So you just have one vertex. And so we have this one surface that's coming together and has one vertex. So there's not going to be any faces. So I see one vertex I don't understand. So that's because so any vertex we have would have to be an original vertex of our polygon. And all of the vertices are identified. They come together under this identification, as I did the kind of vertex chasing just now. So we have just one point. So everything else will just be kind of more smooth. We only have one point that it comes to. And then we just have one face. So then if we write this down, we have 1 minus 4 plus 1 equals 2 minus 2g, which then tells us that the genus is 2. So this L shape is going to look something like this. And if you want to think about as an exercise how to actually fold this thing and identify the pieces to get that, that might be fun for you to do after this talk. Okay, so unfortunately I have very little time. So the L shape is very nice. It's one of the very few shapes that people have actually studied and found the curve associated to it explicitly. And this is because it has a lot of extra symmetries. So these are theorems by Sealwell and Rodriguez, and they actually found the curve that's associated to the L shape with arbitrary side length lambda. So one of the side lengths is 1 and the other one is lambda, and this creates a bunch of different curves. So they found a Riemann matrix associated to lambda and the curve. But this was done only for the L shape. It's hard to use these same techniques in general because this relies on very specific symmetries. So again, we'd like to figure something out that can be used more generally. And our tool for that is called discrete Riemann surfaces, where you put a discrete structure on your Riemann surface. So what that looks like is I start off with, if I started off with a square, I can then put a bunch of black points and white points on it. And then I have some rules that things have to be followed on the surface. So I have a rule for each square, and it's given as a polynomial. And I have a rule that corresponds to the fact that like this point is identified with this point, and this point is identified with this point, and this point is identified with this point. So for each such identification, I also have some equation that has to be satisfied. And in this case, these values where 2 points are identified by translation and I take their difference, that has the same function as the periods. So it's the discrete analog of these integrals that I described earlier, where I integrate I integrate a function, and here that function is f over a period, which in this case is, I guess, a relationship between two identified vertices. So I'm going kind of fast, but the gist of it is, if I put this discrete structure on it, I get a bunch of polynomial equations, of linear equations, actually. And so if I have enough of these linear equations, and then I put some initial conditions on them, I can actually solve this big system of equations and solve it for the values of these periods. And then I can actually put them into a matrix and get what's called a discrete Riemann matrix. And this is studied by Bobenko and Sklepenkov in 2016 for not quite this structure. They used a less nice discrete structure, but then in 2023, Felix Gunther did it for this square subdivision, which is what we ended up using. So they prove that if I do this discrete structure where I solve this big system of equations, if I do it for kind of finer and finer discrete structures where I add more and more black and white points, then eventually I get closer and closer to the actual Riemann matrix of our original surface. So this is kind of an amazing result because these are linear equations that we solve. There's no integration that we're doing at all. And it's a lot easier actually than figuring out what these one forms are on our surface. So if we start with a polygon and we're able to do this, then that's we can actually get very good approximations to the actual Riemann matrix of the surface. And so we decided to put it into practice. And so the rest of the things I'll show you are experiments that we ran. So first we started with the L shape, which was a good candidate because we know what the actual values of the Riemann matrix are from Silhol and Rodriguez. So it's 5/3 minus 4/3 minus 4/3 5/3. And you can see that as, so we did more and more levels of approximation. So 7 means we were dividing into 3 to the 7th squares on each, sorry, 3 to the 14th actually squares in our L shape. And this is the number of seconds that it took for the computation to run. So of course we can't solve by hand such a massive system of equations. These have like millions of linear equations that we can't solve by hand, and we have to do some optimizations to actually be able to solve, to make the computer even solve it. So time is not a matrix. Time is the amount of time it took to calculate, to compute the matrix. So my computer was doing this, and it took 22,000 seconds to get this matrix right here. Yes, this is, I used this block because it didn't take any time to just plug in the values that came from this theorem. So I wanted, okay, where is the theorem? The theorem is here. So that's just this matrix right here instead of time. And I used it because I didn't want to put it into a new block. So this is the decimal approximation of the exact value. But yeah, the computer didn't do this. This one was done by hand, according to Silhol's matrix that he gave us. But you can see that these approximations are actually pretty close. We're getting like 6 digits of accuracy, which is considered good. And in fact, if we know that our numbers are rational, for example, and with and we know that our answers are true up to some precision, then we can actually recover the exact values of the matrix. So this is, I guess, just kind of, it shows that this process works by example. But then we can actually put this into practice for other surfaces that have never been considered as algebraic curves before, or that people haven't, or just don't know what algebraic curves are associated to them. And so we did this for these Jenkins-Strabel representatives, which are, they look like these pretzels. So you have G-1 pretzels, kind of each pretzel contributes a genus, and then this piece attaches back to this piece, and that contributes the last genus. And you can also draw it as this long rectangular strip, also length 4G-4. And you have these kind of weird periodicity relationships. So side 1 is identified with side 1, 2 is identified with 2, and then 3 is identified with 3, which is way over here. And so if you actually think about what the surface looks like, So this will be a genus 3 surface. You can see the relationships are quite complicated. So side 7, for example, this side right here, it lives on the surface like this. And where the alphas and betas actually, their relationship to the sides is kind of difficult to see. So it was actually quite a lot of work to figure out what the surface actually looks like. And the linear equations that we get as a result are way more complicated than they were for the L shape, but still we can do, so this is really easy to divide into a bunch of squares. And we can do this and then write down the system of equations. And so for genus 2, here's what we get. I don't have a last exact row because no one knows what these genus 2 Jenkins-Drabble representatives actually are. But maybe just notice this, just remember a few digits of this, and it shows up again in the genus 3 one. So based on our approximations, we're able to, so we got a bunch of this experimental data, and then we were, so in some cases we can go from the Riemann matrix to the curve, and then we can come up with some conjectures about what these curves actually look like. So all of our computations suggest that the curve looks like this. So now this is a conjecture that now that we know what this curve might look like, or probably does look like, it's just not a proof yet, but the fact that the data shows it to be true isn't a proof yet, but it's pretty convincing data that it's probably true now. This can maybe be attacked by methods similar to, or try to come up with methods similar to Sealhole to actually prove that this is the case. But we can come up with a bunch. So there's a bunch of questions you can ask, and I haven't even scratched the surface of what these questions are. But given our data, we can do a bunch of computations, come up with conjectures such as this one. This is another example of a conjecture in our paper, that the surfaces, that the curves underlying the surface are hyperelliptic, which is, these are also special kinds of curves. So there are elliptic curves that people love. There's also hyperelliptic curves, which are good. But yeah, in general, there are many questions one can ask and experiment with using our methods. So yeah, and in general, so we provide an algorithm that you can follow in practice. It still is hard to follow, but it is easier to follow than it was to follow the literature before. And yeah, you can get this experimental data to find conjectures that you can then work on proving. All right, and that is all I had to talk about. Sorry, I went over time, but thanks for your attention and for your questions.
Yeah, thanks for a great talk. So are there any questions now?
I see a hand. If you want to unmute and ask your question.
I'm not sure how related this is, but you mentioned that you ran like a big part of this topic was actual computations and computing power. So is there by chance, is this topic is a field of math as a whole related by chance to, like, for example, if you have uh an idea for what the Riemann surface is there, forgive me if I'm being vague, I don't know much about it obviously, but is there, will there be aspects of like some problems being easier to check versus like to check if you have a hypothesis about whether their formula matches the actual nature of the Riemann surface? And is there any cases where it's easier to check or something like P versus NP related kind of, if that makes sense?
Yeah, so you do run into these things somewhat. So I guess that's also so related to the Schottky problem, which I mentioned, where you have a Riemann matrix and you want, you have a G by G matrix and you want to know if it even is a Riemann matrix of a surface. So these kinds of these questions have partial answers, I guess, in a way, where there are some things you can say, like sometimes you can say this is definitely not a Riemann matrix. But sometimes you can, so there's a thing you can check where it'll tell you if it's not a Riemann matrix, it might tell you that it's not, but it might not give you an answer. So there are these kinds of things where you have these partial answers. You do run into, I guess, computational complexity issues when you're doing these computations, but mostly for us, it wasn't really anything like P versus NP stuff. It was more just like how do we take a giant system of equations and efficiently compute it so that our process actually terminates within a day. Does that answer your question?
Yes, Miss, it does. Thank you.
Cool. And then it's Gianna, but I saw some questions in chat. So which books would I recommend to learn more about algebraic geometry? Okay, so this depends on your background. There are many books that different people recommend. So Hartshorne is the classic, but I don't recommend it as your first algebraic geometry book. But I do recommend that you read it eventually. When you read algebraic geometry, this is kind of the classic book. Then there's Ravi Vakil's approach, which it goes through kind of category theory more. So and his book is more conversational. So I recommend looking at both of these and seeing which one you prefer. But for more introductory material, so there is Karen Smith's book on algebraic geometry, which you could take a look at. And I will shout out, so my PhD advisor, Bernd Sternfels, writes lots of books. So there's a book called Introduction to Nonlinear Algebra, or Invitation maybe. Invitation to Nonlinear Algebra. And so yeah, there are chapters in this book that are on algebraic geometry, and those I think are good introductory materials and have good exercises in them as well. So it's certain chapters in this book, but yeah, as I said, algebraic geometry is a very broad field. There are different approaches to learning it, and I think just a good way to do it is also to take classes in algebraic geometry from different instructors, because then you get to see different approaches. All right, can I meaningfully define varieties for non-Euclidean algebraic structures? Yeah, so there are different ways you can define varieties. So yeah, so here I guess you're mixing, in this question, you're mixing words a lot with this like path connected stuff. So that's actually not something that is required. You can have many components in your variety that aren't path connected. But yeah, you can think about varieties that start from where you're not working with like Rn or C to the n or whatever, and in fact you do that a lot. All right, I see a raised hand from Gianna.
Are there any known real-life applications of this field of research?
Sorry, can you repeat that?
Are there any known real-life applications of this?
Any known? Well, not that I am aware currently. yeah, for this particular research, I don't know of real life applications for it, unfortunately. But yeah, this is staying kind of just within math, but in general of like algebraic geometry, there are applications to physics. That's something I know about, but yeah, are there connections between algebraic geometry and physics? Yes, there are many connections. So I'm just going to follow up on that because I just got a question in the chat about the connections between algebraic geometry and physics. Yes, there are some very interesting connections between parts of algebraic geometry and physics, and this is actually being studied a lot now. It's an active area of research. That recently they got a big so my advisor, Bernd Sturfels, has been very interested in this. So he, with some physicists, applied for a big grant, and they got a big grant to study something called what they call positive geometry. But this is kind of a new field that is being developed now, but it's basically dealing with algebraic geometry and physics. So specifically things that we can say. So in physics here, I'm talking about particle scattering, particle physics. So scattering amplitudes. So what happens when in the Large Hadron Collider, you send particles to each other and then see what happens. And algebraic geometry, turns out algebraic geometry can help understand some of these processes. Sure, I can share the slides. And what tool did I use for the computations? We used MATLAB to do the computations because MATLAB is good at big linear systems. Is this in I don't know what TQFT is, but I assume the QFT part of it is quantum field theory. Yeah, it's definitely related to that for sure. Yes. Yeah. So if you're interested in this stuff, now is actually a great time to be interested in it because this positive geometry stuff that they just got this grant, it's just kicking off. There's a ton of conferences going on and a lot of people getting into it and working on it now. So yeah, the connections to physics aren't some about the things that aren't about the specific things that I talked about in this talk yet, but with algebraic curves and Riemann surfaces, of course, those. So I guess this talk was largely expository, and all of these things are playing into positive geometry. So if you're interested in physics and algebraic geometry, then now is a good time to be interested in it. So yeah, positive geometry is the keyword, maybe, and also so something that also plays a large role in this is combinatorics. And keywords, there are scattering amplitudes, combinatorics, algebraic geometry, positive geometry, and if you Google these things, you'll see plenty of information about that. All right, any other questions?
Okay, if there are no more questions, let's thank Yelena again. Yeah.
All right, and thanks, you were a great audience. I appreciate all the questions you were asking.
Bye, thank you.